Hello and welcome to the seventh and final lesson in the electricity and magnetism unit. And today's topic is the motor principle. So what's the learning goal? I want you to be able to explain the motor principle and then use it to predict resulting characteristics. So basically predict how a motor will work within inside an electric, like a toy race car. All right. So here's the long-winded kind of definition of the motor principle. Basically says that when two magnetic fields interact, so now we're going to bring two magnetic fields in each other's domain here, a force results. So if a current carrying conductor is placed inside a uniform magnetic field, a force is directed at 90 degrees to both the direction of charge and the uniform magnetic field. So it's like anything else. The definition isn't going to make a lot of sense. So let's go and draw a diagram here to make to help you out with that. So the diagram, it's a three-part diagram here. So let's start with a uniform field. So if I draw a C magnet or two bar magnets that are parallel to each other, like this, and I'll make that the north, not the south, what happens is we have a uniform field. So that's the first part of the motor principle. So we have a uniform field north to south. All right. Next, straight wire conductor. Let's go, I'll go with an X. So it's into the page. So I'm going to take my right thumb. I'm going to put the right thumb on the X. And what results, I'll do this one in red. This is the direction of my circular magnetic field. All right, so there's that. Now what happens when we overlap them? I'm going to make it a little bit larger here, just easier for us to draw. So if you want to fill the remaining space here, just to give us enough room. So I'm going to take that diagram from the first one, and then I'm going to place the second diagram inside. So I'm going to start with the straight wire field. So it is, and we're going to keep it tight. We're not going to use all the space here, overdrawn the thickness of the wire anyway. So let's do maybe 3 rings. All right. So if it's inside there, it's very important to remember that field lines cannot cross. Okay, we talked about it a little bit in class with the electric part. In the magnetic part, it's also true. Field lines cannot cross. So that means that you're going to have your uniform field, which is unaffected, traveling up like that. And then as you get closer to that circular field, the magnetic field lines start to bend like that, so that they don't cross until it goes back to be unaffected. So there we go. That would be how the field lines are. They wouldn't cross each other, so they get squashed in there. And what does, from this, we get a force, okay? So that's what the resultant field would look like. I'm going to talk about what the force, how the force comes from this. So I'm going to come back to this slide in 1 second. So, right hand rule number 3. I want you to open your right hand so that your fingers point in the direction of the field. So I'm just going to draw my right hand, poorly of course, because that's, you know, what I do. So here's my hand, palm up. How many fingers do I have? 4? Something like that? Yes, that's what my hand does look like. All right, so I'm going to put palm right there. So it's palm up. So there we go. So it says that my fingertips point to the north of the uniform field. So what you're going to do is, we're going to draw, if you have another color or pencil, you're going to go a lighter color. So let's just draw a couple parallel lines, crossing my palm, heading this direction to north. So it's a uniform field. That's the same as, if I go back a screen, it's the same as the uniform field here. So basically, there's my cool pen, okay, I've basically put my palm right there with my fingertips. Let's see if I can draw so there's my fingertips, there's my right hand, so my fingertips are pointing toward north inside or between the two bar magnets. All right. What you'll now do is you rotate your hand 360, all right, to make sure your thumb points in the direction of conventional current. So it's like saying, here's the wire that's carrying the current. So I'm going to draw it a little straighter. There's the wire carrying the current. You want your thumb to point in the direction of the current. Okay? So thumb is pointing in that direction. What happens then is we get a force being generated here. And the force is perpendicular to your palm. Okay, so it's like holding the force that's pointing out of your palm. So the force is always perpendicular to your palm. To your palm. Okay, so it's perpendicular to the palm, it's coming straight up. Okay, so if we back up 1 second then, so in that field, the third example here, I'm going to draw my force, I'll do it in blue. So I would have my fingers, and you won't want to draw this, I'm just going to use my magic pen. Okay, so my fingers are going to be facing upward. I've got to rotate that thumb so that it's pointing into the page. So side view is your hands on its side, and here are my fingers all back to back, and the thumb's into the page. I have no idea what that is, but anyway, if you put your thumb on the X with your fingertips pointing upward, the resulting force is this direction right here. Your palm is facing that direction. And again, if you need me to go through and do this in real life in front of you in 3D, not a problem, just ask next day and I'll show you. All right, so there's the third law, and I'm going to come back to it in a second. So applications of the electromagnet, one of it is the scrapyard, the lifting magnet. So basically what they have is they have a large iron chunk at the bottom of the lifting bar. They have two posts connected like that. And what happens is they have a power source, and I'm going to draw it as a DC, even though that's not true whatsoever. Hooked to a switch. And then the wire comes down and coils around and then goes to the other side. So the way it's coiled, if we use our second law, the coil one, so our flow of electrons are going this direction right now. So that means that I would grab it with my thumb pointing up. That would mean right now this bar has a north and a south, which means that this large piece of iron has a south end here. The wire then is wrapped around the other post, but we need to make the large chunk of iron a north end there to make it a proper magnet. So that means I need to make sure that I wrap the wire so that my thumb will be pointing down, and in order to do that, I've got to coil it back around like this. And it returns back to the source. So then if you grab it, you see that I would grab it, my thumb would be pointing downward, which would make this north, which makes this south. And that switch that we have up here turns the magnet on and off. So as soon as the switch is open, that large chunk of iron is not magnetized and you can drop stuff. So that's how that electromagnet works with that wrapped coil combination. So anything that it's in contact with becomes magnetized. So this region here, if the bottom of that post, is south, that means that it becomes south at that end of the bar magnet. And the nice thing with electromagnets, as soon as that switch is opened, this isn't magnetized anymore. It's done. It's just a chunk of iron. That's how stuff will drop. Moving along, Faraday's law of electromagnetic induction. So that's a mouthful. So we just call it Faraday's law. States that magnetic fields that is moving or changing in intensity near a conductor causes or induces electron flow in the conductor. What does that mean? Basically, what happens is that I'm just going to have, these are just going to be two boxes. All right. And in the boxes, we have, Oersted. That's what I'm trying to write there. Oersted. And on this side we have Faraday. And what they say is that, or what Ørsted says, draw an arrow, looking arrow. Ørsted says that, hey, I can create a magnetic field. So I can create a magnetic field with electricity. So basically what Faraday said is he's got a returning arrow coming back that says I can create current with magnets, which means it goes both ways then. If you can create a magnetic field, you can create electricity. If you can generate electricity, you can create a magnet. So they go hand in hand. So then this allows what we another physicist, Lenz, to say that we can induce the electric flow. So what he said was, if we have a coil wrapped around a bar, so that's what we have here, and we take a magnet, so here's my magnet, and if I rotate it, the arrow direction of the arrow, so it's basically saying I'm taking this magnet, I'll lift it off, I pass it across, lift it off, and so I create this circular motion like this. Whee! I know, it's awesome, isn't it? I go round and around. Anyway, so what happens if I rotate that magnet in that direction, what happens is that the piece of metal inside gets magnetically induced, which would mean that if I pass it in this direction with the magnet in that orientation, that I end up with this end becoming north, all right, this end becoming south. So if that gets magnetized, that will induce electron flow. So then I put my thumb toward the north, and it tells me the direction of current, so my fingers are reaching over top, which means that electrons are being moved, and it means I have current flow. So if I pass a magnet over a coil, I can create electricity. All right? Then, if Lenz said if you go the other way, so you go like this, whee! So I'm looking at the bottom coil now, so I can move that down a little bit. So basically, I am, oops, got my magnet, I'm going like this now. So I rotate the opposite direction. If you rotate the opposite direction, obviously, or I shouldn't say obviously, intuitively, whoops, I'm not sure what M is, north. There we go. That becomes north, that becomes south. Now you got to grab it the other direction. So now it shows current going underneath in the direction of my fingers, which means that it's now curling in this direction, which means I've now changed the direction of the electron flow, or the current. So that's what Lenz came up with inducing flow. So if he has a magnet passing over a coil, we can create electrical flow. If we have electrical flow in a coil, we can create a magnet. So it's that that combination of being able to go back and forth, which allows us to create the electric motor. So we're going to finish up this this particular lesson in the next video, and we'll move on from there. So I'll see you in a minute.